Welcome back. It's been a while. Lots of things have changed since the last video I made, but what hasn't changed is that I still like math, and I'm going to be showing you some today. But what has changed is that everyone's attention span has gotten shorter. So what I'm going to be doing is, instead of going through all the laborious computation that I do in my normal videos, which causes them to be, over an hour long, I'm going to skip some of it, just state that, this becomes this. And if you want to work out the details, I'll leave that up to you, which may actually be helpful, so that, you can draw some of the conclusions yourself, and instead of me just sort of feeding you all the results. Yeah, and this particular topic, I'm going to split into 2 videos as opposed to 1, so that'll make it even shorter. Yeah, and I think you'll see it's kind of logical to split this into 2 separate videos, so that's okay. What I'll also do is I'll give you a practice problem at the end to try yourself, so that you can, practice the technique I show in this video on a similar integral, and then, get your result, and then I'll show the answer in the next video, basically. Is there anything else I need to say? Yeah, also, obviously, splitting it into 2 videos might help me farm viewership off of you guys, since you have to watch 2 instead of 1. But that's okay. That doesn't violate my morals. Yeah, okay, let's begin. So we're going to be looking at arctangent of r e to the I theta. So that means any complex number. We're going to treat r as greater than or equal to 0. I'm going to say that at the start because it's relevant. And theta obviously is just an angle. So this represents any complex number in polar form, but it gives us 2 degrees of freedom that we can work with. So I sort of have to introduce this function first, because there's some property of it that is very relevant to how we treat the integrals we get. So I have to introduce that first, and then I'll get into the actual problem. Basically, what's going to happen is that by taking some of the terms involved with the arctangent, we're going to be able to get formulas for non-elementary integrals despite not actually doing any non-elementary integration, which I think is very cool. You get basically free results for difficult integrals. Yeah, okay. So we can start off by rewriting arctangent using its complex logarithm definition, which looks like this. I was about to write a t theta. Yeah, so like that. Now we can go even further because we know how to expand complex logarithms, so we can do that for both terms. Let's look at the first one. So, as you know, a complex logarithm is equal to the logarithm of the modulus plus I times the argument of the complex number. So, log of the modulus is just the real part squared plus the imaginary part squared, square rooted. But for a logarithm, you can pull that square root out as a 1/2. So we're going to have 1/2 ln. This is one of the times where I'll just skip the computation. I'll tell you that the modulus of this will end up being 1 plus r squared plus 2r sine theta. And now we need plus I times the argument, which in this case we'll just use a real value arctangent. The real part, so we need the imaginary part over the real part. The imaginary part here clearly is going to be minus r cosine theta. And the real part, we'll have this 1, and then we'll have a minus I going into I sine theta, which is just going to give us a 1. So that's 1 plus r sine theta. Yeah. And then something similar for this, we have to subtract. The modulus will be the same, except we have a minus. Again, you can verify this yourself easily. And then we have a minus I arctangent, because again, we're subtracting. The real part is r cosine theta, no negative this time. but where the negative went is here, because the real part is 1 minus r sine theta. Okay, and this is all in the multiplied by this. So now what we can do is let's group the similar terms together, pull in this I over 2. So that means we're going to have I over 4, and I'll use logarithm properties just so I can make the expression a little bit shorter. And then, okay, I don't really need parentheses here though. And then here, notice arctangent's odd, so the minus is going to come out, but I times minus I just gives us a positive. And also notice here that we just have a raw minus I, so I times minus I gives us a positive. So that means we're going to have 1/2 that we can factor out. Yeah, okay. There's not much we can do to simplify this, but there is actually a formula that lets us, rewrite the sum of two arctangents as the arctangent of a function of the arguments. That formula is this. This. So obviously this is A, this is B, or actually it doesn't matter what the order is. So now basically you just have to compute this term using this. It takes a second, it's just computation. So again, I'll skip that, and I'll just tell you that, excuse me, that this ends up being arctangent of 2r cosine theta over 1 minus r squared. That's what this becomes after all the simplifications. Okay, great. But now we obviously see a glaring issue here. Can you guess what I'm going to say? Yes, r equals 1. Because remember we said r greater than or equal to 0. So -1 we don't consider. Although, for future reference, all the situations with like -r are basically analogous to the positive r situation, but just it's simpler if you just think of r as a magnitude, because you don't really need to think of it as anything else. Yeah, so we have an issue at 1. Now, the thing is, you might think, oh, but arctangent has values like in the limiting cases, so that should be okay. Not entirely true here, because think of it. Let's say r approaches 1 from the left. That means the denominator has been positive. So that means the 1 over 0 that we get here corresponds to positive infinity. So that means, given this cosine theta, because this still varies with theta, so if we're in the right half of the complex plane and r is approaching 1 from the left, then we'll have a positive infinity in here, which will give us a pi over 2 and thus a pi over 4. If we're in the left half, it'll be a minus in here because cosine will be minus. But if r is approaching 1 from the right, then that means this denominator has been negative, and then you still have to consider cosine theta, which means in the right half of the complex plane, you have when r approaches 1 from the left, and you're in the right half, that means you're approaching positive pi over 4, because this 1/2 just makes it pi over 4. Whereas if you're approaching from the right, that means you're approaching negative pi over 4. So that's just a straight up discontinuity, like no issue about it, that's a discontinuity. So technically what you have to do is you have to define the function piecewise, and then to this term, like if you ignore the 1/2, you have to add a multiple of pi depending on whether cosine theta is positive or negative, and depending on if r is greater than 1 or less than 1. That's how you would make it continuous. This isn't really relevant to what I'm going to be doing, but it's still useful to just think about, because obviously this is discontinuous. But what I want you to take away from this is that we have to treat the cases where r is less than 1 and where r is greater than 1 separately, because we know that there is like an issue at r equals 1. We know that there's something discontinuous, so we have to treat those cases separately because our integrals and formulas will behave differently, in those two different regions. So yeah, that's pretty much all of like the introduction for this function I needed to give, because this is just the important part, basically. I mean, the other stuff is important, as we'll see, but this was important in terms of how we conceptually think about this. Okay, now what I'm going to do, I said that our arctangent is going to give us some formulas for free, basically. I'm not going to be integrating arctangent itself, but rather one of its components, one of the logarithmic components. Now I'm just going to choose this one because this is simpler to work with, as you'll see. It doesn't really matter though. Basically, all the cases will end up being symmetric, and they'll usually equal each other. So it won't be that big a deal, but I'm just going to work with this one to start off. And I'll show you how to get free integral formulas. Okay, so remember that the real part of this, hold on, let me make sure I'm still recording. I've made this mistake too many times. The real part of this was equal to this. Not cosine. Okay, so that means if we integrate both sides, then we'll get the same thing, naturally. So that means, let's look at the left-hand side. Let's integrate from 0 to 2 pi with respect to theta. That seems natural. Okay, you could technically stop here and realize what this becomes, but I'm going to keep working through it just because, yeah, because this is a complex function, you can think of it as an integral over the unit circle, which is a closed contour, and there shouldn't be any issues here because r is always less than 1, so your complex number is has magnitude less than 1, modulus less than 1. So you should know what this equals, but I'll work through it. It's only a couple of steps. First, okay, by the way, real part is linear, so you can just pull it out. So, but also remember that ln 1 minus x equals this. Equals that. We're going to use that. So remember that only works if x was had absolute value less than 1. Now, conveniently, we didn't say yet, but I'm going to say now, we're going to look at the case where r is less than 1. So that means we're inside the unit disk in the complex plane. So that means r e to the I theta, r e to the I theta is always going to have modulus less than 1. We can make this integral a little bit easier because this I can be moved into the theta as theta plus pi over 2. So that means we want theta goes to theta minus pi over 2. So this means we have real part, which I said we could pull out. It's going to be from pi over 2 to 5 pi over 2. The I goes away. Okay, now we can expand this using the series. So this becomes minus real part. Now, of course, anything related to theta has to stay inside the integral, but the r will be part of the x to the k. So that means r to the k can be pulled out because it's independent of theta. And this will just be e to the ik theta. Okay. We can, if you need help seeing it even more, we can remove the real part to turn this into cosine k theta. And you should know that this is just an integral of cosine over the full period, so 0. Okay, nice. So this whole thing equals 0. And what did that tell us? That told us that, actually I should erase this first. That tells us that 0 equals this. And I hope you know 1/2 isn't 0, so I'll make this go away. Yeah, so this should already be like sort of interesting to you, just because r can be anything less than 1, but somehow anything of this form will always integrate to 0. It's kind of neat, right? So yeah, this doesn't seem very useful, right? Like, okay, we got 0 equals this integral, and our integrand is like really specific. Like, how are you going to notice you have an integral of the form 1 plus r squared plus 2r sine theta? So that's the objective. We have a result for an integral. It's not one we want, but we're going to transform it into one we want. I'll show you how to do that. So this is the same as if we pulled out a 1 plus r squared. Okay, makes sense? Just logarithm rules, cool. This is independent of theta, so we know what that evaluates to, and that we can actually just move over to the other side because it all equals 0. So that means, actually I can do this. So it's just going to be minus 2 pi ln 1 plus r squared. Okay, it looks a little bit better. At least we have like a non-zero result for an integral that's at least, it looks a little cleaner because we have 1 plus a coefficient times sine theta. But still, how are you going to know that your, your integrand is of this form? So we're going to make it more explicit so that the formula looks nicer and the integral looks nicer. So here's the trick. We're going to let 2r over 1 plus r squared equal alpha. I'm sure this is like a well-known trick, but like when I thought of this, you know, just when I was solving it, and I was really proud of myself, like for making this little trick, because you'll see what I mean. Basically, we want this to be this 2r over 1 plus r squared. We'd rather solve for the integral of ln 1 plus some coefficient times sine theta, where our coefficient is just like in terms of one symbol, like alpha, instead of this nasty fraction. So we want to make this alpha, but we have an integral in terms of r. We have a formula for it in terms of r. So we turn this integral in terms of alpha, but that means we also have to transform the, the result in terms of alpha. Or transform the result from r to alpha. So that means we have to solve for r, which is actually simple. So our equation right there, actually, before I do that, observe, I'll just do a quick proof of this. This is always greater than or equal to 0, but, so this is for all r, this is greater than or equal to 0, and only for r that is not 1, this is greater than 0. So only at 1 does this term actually become 0, obviously. But this just implies 1 plus r squared is 2r is greater than 0, or minus 2r. That. So this holds, and this should make sense, actually, that this term right here is less than 1, if you think about it, because if you're on the interval 0 to 2 pi, just think what happens at theta equals 3 pi over 2, because sine will be minus 1, and if you have a coefficient that's greater than 1, then that's a negative of greater magnitude than just 1, so that means you're going to have ln of a negative, which is bad. Yeah, and because this is supposed to be the real part of a complex logarithm, so you shouldn't have anything imaginary here. So this just verifies our intuition, but now let's actually solve for r using this. So we have that 2r must equal alpha plus alpha r squared, implies alpha r squared minus 2r plus alpha equals 0. All right, solving for r, quadratic formula, you know how it goes. Minus b, that's 2, plus minus square root b squared, that's 4, minus 4ac, that's 4 alpha squared, over 2a, 2 alpha. Okay, this can be simplified. Bam. Problem is, we have two options, right? But here is where our condition of r less than 1 helps. Because notice that if alpha is less than 1, when we have 1 plus square root 1 minus alpha squared, this is just 1 plus some positive number divided by a number that is less than 1. Therefore, that will be greater than 1. And since we're solving for r, we know that can't be, because we know r is less than 1, so that means this, the one with a minus, is the only valid option. And that equals r. Okay, now what do? We wanted to rewrite this r squared plus 1 in terms of alpha, so that'll give us a formula in terms of alpha. Now you could square it and add 1, but there's actually a simpler trick. Notice that by our definition, 1 plus r squared is the same as 2r over alpha. And since we have r already, that just means 1 plus r squared just equal to 2, 1 minus square root 1 minus alpha squared over alpha squared, right? But we can simplify this. Let's just quickly multiply by the conjugate up here. Okay, now notice this is a difference of squares, so that's going to be 1 minus alpha squared, which just ends up being positive alpha squared. So that means all of these terms cancel, and that just leaves us with 2 over 1 plus square root 1 minus alpha squared. Okay, nice. And notice in the formula here we have a minus, but we can bring that into the logarithm just to invert this, so that at least this term comes into the numerator. So what does this mean? Actually, I should probably write it down here. This means, nice and big for everyone to see, because this became alpha, and now we have our result in terms of alpha. Bam. This is a non-elementary integral, which we got the result for without actually solving a non-elementary integral, which is pretty cool. And it's generalized. I like doing generalized stuff, as you know. So you won't see anything that's not generalized anymore from me. That's in the past. Yeah, so that's pretty cool, right? Like, just from looking at this simple integral, which we knew evaluated to 0, we were able to then get a result for an integral in terms of r, and then transform variables into alpha, so that we have a nicer looking integral, because this looks more general, right? You can plug in any alpha, which I should say, since we defined it for r less than 1, that means alpha is also less than 1, but same for r greater than 1. Although I will say this does actually hold for alpha equals 1. So I'll just put that there. Basically, the point is we have to ignore r equals 1 until, like, we basically have to go on a case-by-case basis. Like, check if the r equals 1 case actually works. And the only time alpha could be 1 was if r equals 1. So in this case, it does work. You can verify it yourself. Like, if alpha is 1, this term becomes 1, so that's going to go away. So you'll just have minus 2 pi ln 2. Yeah. And notice alpha can be negative because the situations are actually symmetric. Think if you go theta goes to 2 pi minus theta, you'll get the same thing, but sign is negative, so you'll have a minus out here. And actually, if you work all the way back, you'll realize the minus problem with minus alpha would be the same thing as if we started with 1 plus r squared minus 2r sine theta, which, remember, was the real part of the logarithm of 1 plus I r e to the I theta, which was the other part of arctangent. So that's what I was saying, where like the cases are actually the same, but you just can't see it immediately. So that's why only working with 1 is valid, or it is useful. Because if we looked at the logarithm of the quotient of the moduli, what is it? That's just a difference of logarithms, and since they're the same thing, that would have given us 0, but that would have given us a non-meaningful 0. That would have just told us that those are equal and not actually give us the result for either. Yeah. So yeah, we got a free formula just from looking at complex arctangent. Now, one thing I typically do is, or at least here, since you get like this result for free, you have to be a little bit skeptical just to, verify it if you want to be thorough. So I integrated this using contour integration as well, like directly, like skip the r part, just this integral right here, get the answer by basically treating this as another parameter, differentiate with respect to it, integrate from 0 to alpha, and so basically make it a double integral and then contour integration along the unit circle, and then bam, you're good. You'll get the exact same thing. Okay, and another thing I thought when I got this result was, can we get a better result? Or maybe not better, but can we get a result with like different bounds? Because we have it along the whole period. Can we do like a half period or something? Okay, let's think about that. Okay, so now I think the most logical way to split this is, okay, let's pick the theta values, the theta range that allows sine to take on its full range of values. So in that case, that would be minus pi over 2 to pi over 2. That's where sine goes from minus 1 to 1, takes on all its values. So intuitively, if we're integrating from 0 to 2 pi, that range right there from minus pi over 2 to pi over 2 should give us just half of the integral from 0 to 2 pi. So our hypothesis is, does this, so same integrand because we're dealing with sine, does this equal 1/2 of what's down here? So, I mean, it's easy to get the answer, but it's not like immediate, because if you naively try to shift the bounds of this integral to match like this pi over 2 shift, well, you've screwed yourself, because this is going to turn into a cosine, and then that's not a cosine. But actually, the answer is yes. This is just 1/2 of this, and you can show it by basically manipulating the bounds here and playing with it that way. I'll leave that to you. That should be just a neat little quick exercise you can do to show that, this is just 2 times of an integral along the theta range that lets theta take on all its values. Not theta, sine. Yeah, so I'll just state that this is true, and then you can prove it yourself if you want. So that means this is just 1/2 of this. Okay, and also notice that by shifting by pi over 2, you can get that this is which should make sense because it's the exact same case as here. 0 to pi is where cosine takes all its values. So it should be just half of this. So yeah, this also holds. So that's another couple of results we get from this. By the way, technically, we can do this. Can I? Yeah, we can do this. Because theta goes to pi minus theta gives you the same thing. So I'll actually tidy this up. Yeah, the integrals all evaluate to the same thing because an easy substitution like here, x goes to minus x. Or sorry, theta goes to minus theta. Theta goes to pi minus theta. Theta goes to 2 pi minus theta. These will all give you the result with the minus sign. So it's the same thing. Now, you might be thinking, well, okay, we were able to basically cut the theta range in half once, so why don't we try to do it again? Can we get the integral from 0 to pi over 2 of one of these? Which, notice, along these bounds, this is the same as if you just replace this with a cosine. That's bad theta. Okay, short answer, no. This result will not help you with this, because this is special. Now, let me tell you why. When I first saw this, and I thought of it, I knew almost right off the bat that this would not have a nice closed form, which in fact, it does not. Or at least I haven't been able to solve for it, and I don't think it is one. Because basically, if you look at one of my previous videos, I solved the integral from 0 to pi over 2 of ln 1 plus sine theta d theta, aka the alpha equals 1 case. But the result ended up containing Catalan's constant, which came from an infinite series that we had to evaluate at some point. But the issue is, for general alpha, like, that's not necessarily equal to 1. That sum, I figured, was probably not going to take a nice value, like Catalan's constant or some other well-known constant. So my intuition was that this would evaluate to an infinite sum, as opposed to a nice closed form, at least that we can find. And in fact, I was right. So now, this is the homework problem I will give you. Use the same technique that I used on the integral from 0 to 2 pi to get the series representation of this integral. In other words, take that log 1 minus re to the I theta, 1 minus I re to the I theta term, integrate its real part from 0 to pi over 2. You'll get a formula in terms of r, and then do the same trick where we, separate the 1 plus r squared, and then change variables into alpha. So do that, and you'll get an infinite series representation of this integral. I mean, it's messy. It's not like horribly messy, but it's not nice, I would say. Yeah. And like I said before, I always try to verify the results a second way, like by properly integrating the function as opposed to using some like indirect tool. So in fact, there is another way to solve this. It took me a second to like figure it out, but I don't think there's actually another way to do it. Like, besides the logarithm trick and then the trick I used, I'll give you a hint. Basically, Fourier series. That's the only other thing that I think will crack this integral and give you the result you desire. Yeah, because I don't think anything else works. Like, immediate contour integration doesn't work just because your bounds aren't like any 0 to 2 pi stuff, so you can't integrate over the unit circle just yet. So my hint to you is to use Fourier series and try to verify that same result that you got from using the technique I showed you a different way. And in theory, those should be equal. And yeah, so basically solve it the indirect way and then solve it the direct way. It is a bit computationally heavy to do it the Fourier series route, but it is more direct. And I don't know, it's good practice because not only will you use Fourier series, but you'll also use contour integration later. Yeah. So I'll show the answer to this problem in the next video, at the start of the next video. And yeah, I don't think there's much else to say. We got technically 6, considering the plus minus, but we'll just say 3 actual nice formulas, just without doing any non-elementary integration, just from analyzing complex arctangent. So yeah, I think that's pretty sweet. Yeah, how am I doing on time? 35, yeah. Okay, shorter than my usual videos, but not too short. But hopefully you appreciate my effort that I put in to try to speed this up. Look at all my notes. Yeah, one thing I should note is that we only looked at r less than 1, but for this case, the r greater than 1 case will, it'll give you the exact same thing. Your steps will be slightly different. Like for example, when solving the quadratic equation for r, you'll have to use the positive root instead of the negative root, or the root with the plus instead of the one with the minus. But inevitably, you won't be able to get any different result from that. You'll just get this same result into this. So basically, it'll just give you the same thing. It's just taking